Okay, good morning, everyone. Today we continue our discussion on ransomware techniques and how we can test a security solution if this anti-ransomware module or behavior blocker of antivirus can detect a ransomware attack. And we'll talk about ransomware attacks, about AI, and in particular reinforcement learning as a method of machine learning that can be applied in security testing to test how good some specific antivirus solution is. In the previous episode, we talked about AI and ML capabilities to detect ransomware attack. We got familiar with Locker, Goga, and Mega Cortex ransomware attacks. Those were targeted attacks, pretty much sophisticated, and we also discussed how these attacks leveraged ransomware bypassing techniques. And today I am going to give you a small update. So what happened since the last webinar. And the attack that I'm going to talk is Wasted Locker. So Wasted Locker is an advanced piece of ransomware seen in at least 31 publicly known targeted attacks operated by the Evil Corp. It's a Russian cybercrime gang against US-based corporations since May 2020. The most recent attack was against Garmin, in consequences of which a Garmin Connect service went down. And the ransomware demands typically vary from $500,000 to over $10 million in Bitcoin. What's interesting in this attack, so why we actually choose it for consideration, is how Wasted Locker, which particular techniques Wasted Locker used for privilege escalation and defense evasion. In particular, Wasted Locker had a digital certificate, so the binary was signed. It used legitimate Windows application winsat.exe to leverage auto elevation. So as a result of this auto elevation technique, Wasted Locker managed to copy itself to Windows folder and start itself with higher privileges. Also, DLL side loading. So winsat.exe process loaded winmm.dll, but the DLL was actually compromised. So the content of this DLL was different. It was malicious, not the original one. And this is called DLL side loading. And to hide the payload stored on the disk, Wasted Locker used alternate data streams. Probably you've seen when some data are stored not in files, but in a special data structure in network file system, NTFS. And because of that, you cannot find it, this ransomware, this malicious payload in your file system in Explorer. And the last thing, which actually made most of anti-ransomware modules blind, especially those that work with based on a behavior blocker, is a file memory mapping. So Wasted Locker mapped the user's file into the memory, then encrypted content, and then the cache manager, when it figure out that the file is dirty means like the content of the file has been changed and it needs to be synced to the disk. So a cache manager, Windows Cache Manager, roll this change to the drive. The thing is, the actual ransomware process closed the handle to the file before this modification, and this modification in monitor are done by system. And this is why, for example, behavior blockers cannot recognize suspicious activity performed by this ransomware process. So behavior blockers can see only modifications done by the system, by cache manager. So I would like to start today's presentation with the Winston Churchill quote: "Generals are always prepared to fight the last war." Translating to our domain, it means that anti-malware vendors and testers are mostly focused on detecting known threats. For example, okay, sorry, I just need to sync my slides. Just a second. So this is a quotes by Winston Churchill, and we go next. And here we have how MITRE addressed the problem of detecting possible future threats. And MITRE used attack simulation. So my hypothesis here is that it is possible to create a ransomware simulation that will use an arbitrary combination of known tactics and techniques to bypass an antivirus. To support this point, I put this diagram published by one of the tested vendors that shows the latest MITRE attack evaluation results representing APT29 attack simulation, where every bar represents the detection results of a specific anti-malware solution. As you can see, the number of discovered tactics and techniques varies from vendor to vendor, even for the known threats. So tactic is green and technique is dark green. So here we have these numbers, and they can see the size of these bars are different. So here the question arises, what would be if we don't stick to a particular threat actor, such as APT29, but choose an arbitrary combination of tactics and techniques to represent an imaginary advanced persistent threat, not yet discovered. And the second question is how to select the set of tactics and techniques that will be able to bypass anti-malware protection by specific vendors. So these two questions will be our discussion points for today's webinar. And I would like to present a small demo, actually, how we can leverage attack simulation, in particular to simulate ransomware behavior. So here we have ransomware simulators that we created. We open the folder with the files that ransomware typically encrypts: documents, pictures, videos, and so on, text files. Then we configure it. We specify algorithm, crypto library, extension, and what is important, the number of files. We encrypt one file, then one more file, then one more, and this activity is not detected. But when we change the number of files to be encrypted to 5, we can see that our anti-ransomware detection script, written in Python for this simulation, detects that we have a ransomware activity in our system. And if you take a look at the log, you will find that there are like 5 files modified simultaneously, and we have a timestamp for these files, modification timestamp similar to all of these files, which is suspicious because user typically do not modify like many files at once. So this is how we can simulate ransomware attack in our environment. And the next step is actually how we implement reinforcement learning. So to start, I think I need to introduce what reinforcement learning is. So we came to the idea of putting a brain into the ransomware simulator with reinforcement learning that should be well known to real-time strategy games such as StarCraft. Agent performs actions that affect in some way environment. So in our case, our action is encryption. So we encrypt using different techniques. So we choose the techniques that should be used in particular iteration of encryption. Then our agent is ransomware. It's a simulation of ransomware, and environment is our operating system. So this is where we have our files and these files to be encrypted. Then after we execute ransomware, and this ransomware tries to encrypt files in the environment, in our operating system, in the folder, then we can evaluate the next state of this environment. So this state can be evaluated, for example, in our case, by the number of encrypted files. Let's state it as an enc. And reward will be some numerical evaluation, how good this action was, how successful the action was. And in this particular case, we can denote that reward will be, for example, 2 multiplied by the number of encrypted files minus 1. Minus 1 means we need to deduct some score because we run this iteration which takes some resources, and so we need to minimize the number of actions to encrypt all the files. We're going to talk about the reward function a little bit later. And based on this iteration, we can update our Q table. Q table is our brain in reinforcement learning. It contains of Q values. Q stands for quality. And these Q values, they reflect not only how successful the previous action was, take into account the reward obtained during this action, but also what will be the rewards for the next step. So the Q table represents not only current state situation, but also takes a look in the future and try to build a long-term strategy. So this is the idea of reinforcement learning. So we focus not only on current results, but we try to build long-term strategy. We need to find a policy that will maximize our reward function, and in the end we achieve in our particular case we'll encrypt all our files. And you probably heard about AlphaGo and AlphaZero algorithms developed by DeepMind. It's a UK startup that defeated the Go 18-time world champion Lee Sedol that you can see on the picture. In Go game, it is impossible to trace all possible moves, which is 10 by 360. So you cannot win by simply applying brute force. This is a good example where we can apply reinforcement learning, and DeepMind did it, and pretty much successful. So what actors we have in our simulation, in our experiment? So we have first actor is a ransomware simulator. It's our agent. So the goal of the ransomware simulator is to encrypt the maximum number of files in the minimal number of steps. And we have 3 different options in how we can encrypt to hide this activity or just do it in some specific way. The first option is to add a specific extension to the file, to the encrypted file, for example, .enc. The second option is we use base 64 encoding over A as encrypted data. And the third option is we can select the number of files to be encrypted per iteration. On the other hand, we have another agent called Ransomware Detector. So the goal of the detector is to detect files encryption and generate an alert to user. And in defense solution, this module should also block the ransomware and prevent files from being encrypted. And our ransomware detector has three methods how to detect ransomware activity. The first one is checking for the second extension. This is what we have in the first option for agent. The second is entropy level evaluation. It also connected to base64 encoding. If we use base64 encoding, it affects entropy, which goes down, and this makes the encryption undetectable. And the third option of a ransomware detector is detecting anomalous files modification timestamp. This is what you saw in the demo, in the ransomware simulator demo. Let's go further. And here we have some definition for what states are in our model, actions and rewards. So we have states from 0 to 10, which means 0 means 0 files encrypted, and 10 means all files, all 10 files encrypted. So the goal of ransomware simulator or our agent is to encrypt all files in the minimum number of steps. The rewards, as I already mentioned, the reward function can be calculated as the number of encrypted files multiplied by 2 minus 1. Minus 1 is the cost of the iteration. Actions we have based on possible combinations based on 3 options available: adding extension, base64 encoding, and the number of encrypted files. We have 16 possible actions, and we can see all these actions encoded in the table that represents whether one of these features, extension, base64, number of files, is enabled in this particular step, in this particular action. And this is how we calculated, how we denoted these actions. So again, if we go back to this picture, so now we understand the states, the number of states. We have 11 states. We understand what reward function is, and we also know that there are 16 possible combinations of the actions that our agent can perform to simulate ransomware. And here you can see some results obtained during the experiment. And this is a diagram that shows rewards versus game. Game means it's number of iterations that lead to success or to the fail. So the consequence of every game is whether all files are encrypted or the ransomware activity was detected by the anti-ransomware script. And in this case, we can see with the game progression, we can see that the rewards actually goes up, and in the end, when we have like after, let's say, 500 games played, we can see that our agent is smart enough to get the maximum reward possible in this experiment. It's reward equal 15, which means the other 5 reward scores, they were used, they were deducted because of 5 steps. So reward equal to 15 that were achieved in 5 steps. So 10 files were encrypted in 5 steps. This is how it can be seen, the correlation, the dependency between wins and games. So in how many games our agent was able to encrypt all 10 files. And we can see that the number of wins goes up exponentially. And another diagram that shows the wins rate. So how many wins we have per 10 games. And it also goes up exponentially while it comes to 600 games. And let's take a look at our Q table. As I said, Q table is actually brain of our agent. So this is how our agent makes a decision which particular action to choose. There are at least we can use different strategies that are called policies. For example, one policy, when we have this Q table empty, when we have all zeros in this table, is a random policy. So we choose the actions randomly on every iteration. Then once we have some values already defined in this table, we can start using, in some cases, we can select the best option based on the value, Q value in this table. So typically, we start our simulation, our training from using completely random selection for actions. And then after each step, we reduce the randomness and increase the probability of choosing the action based on Q value that we have in our table. And till the end of the training, we'll slightly switch from random policy to so-called accountant policy, which relies only on Q values in our table. So let's take a look. This is after the training. We have this following table. So let's try to find out how our agent behaves and what the best strategy our agent identified. So in state 0, when we have none of the files encrypted, the highest Q value states that we need to choose action 14. And if we go back to our table, we know that action 14 is we use extension, so we add extra extension. We use base64 for encoding encrypted data, and we encrypt 2 files per iteration. Let me sync again with the yeah, it's synced again. So we select action number 14, which means we encrypt 2 files in this. Sorry, not 2 files, but 5 files. So we go from the state 0 to state 5, where we have 5 files encrypted. And then we actually choose the best action based on the Q value, and the highest Q value we have for 5.49 for action number 1. And action number 1, if we go to the table with actions, so action number 1 is encrypting 1 files and with extension, without extension, and without base64 encoding. So we go back to this state, and we encrypt from here. We encrypt 2 files and go to the state 7, where we have 7 files encrypted. Then we choose here the best action, which is action 0, which encrypts 1 file, and we go to the state 8. And here we have a threshold, which means we designed our anti-ransomware script to detect the ransomware activity if we can see 8 files modified simultaneously, or so we set up a threshold 8 files suspiciously modified that will trigger an alert in our case. And from state 8, we choose again action 0, and we encrypt 1 more file, and we go to state 9. And here we choose action 2, which encrypts 5 files. Actually, at this stage, we don't care how many files we encrypt because we have only 1 file left. And if we compare the action selected here in the beginning and in the end, we can see that 5 files were encrypted using base 64, and we can say that 5 files is less than 8, less than our threshold. And then we switch to another strategy. We do not use base 64, so we encrypt files without base 64 encoding. So our script can detect the high level of entropy. But again, we have 5 files here, 5 files here that were encrypted without base 64. But still 5 files is less than our threshold. So we have 5 files in the beginning encoded with base 64 to decrease the level of entropy. And here we have 5 files encrypted without decreasing the entropy. And again, we encrypted these files we split the encryption. We didn't encrypt, our agent didn't encrypt all files at once, because otherwise 10 files will exceed our threshold and our anti-ransomware script will detect the attack. So in this case, we split the encryption of 10 files in several iterations to prolong the encryption time and make it not so suspicious to our anti-ransomware detection script. So this is how Qtable is used in reinforcement learning. So this is how you can train your agent to find the optimal strategy to get the maximum reward in the end and achieve the goal encrypting the files. So this research is in progress. So currently I'm working on testing reinforcement learning, security testing with reinforcement learning on real anti-malware solutions, antiviruses, EDR solutions. And the second interesting thing is I investigate the possibility to apply this reinforcement learning in security testing in network and web penetration security testing. Actually, I've seen a couple of works from 2018 where the authors, they applied this reinforcement learning to train the security agent that executes cyber attack against the network or against the web service, and try to choose the best way how to propagate in the target environment in order not to attract attention from the defense solutions, as well as be able to achieve some valuable information assets in the compromised network in the minimum number of steps. And few words about our project that we are currently engaged is PROMIS, which is about development of cybersecurity courses. And so those courses, they are university-grade courses, but they are designed not only for students, but for engineers, for professionals. They are made for distance learning. So you can take the course and choose the pace that is convenient for you. And if you're interested, you can contact Anna Eriksson if you want to apply. And currently we have been working on 3 courses. The first one is security in software-intensive products and service development. This course is focused on security development lifecycle. So how to introduce security steps, how to introduce security checks and the procedures into the life cycle of software development. The second course is software security. So here we have a focus on attacks against software and how to implement techniques in the code, how to protect the code of the software against such cyber attack, how to make your code attack proof and protect against compromise from the attackers. And the third course is web system security. It's considers the same problem but against web application, web services. So how to protect your web services against cyber attacks. And finally, so to apply for this course, you need to have at least 120 credits, or you need to have at least 2 years of professional experience. So again, this course, it's a master course for students as well as for engineers. So if you work for 2 years and you are good enough with you understand the software development life cycle, so you are welcome to join and to get knowledge and skills how to introduce security into software development life cycle and use best practices in your work. So that's all. Thank you for attending this seminar during the summertime. I understand that most of you are still on vacation. And if you have any questions, I will be happy to answer.